How's it going, guys? Welcome back. First of all, before we continue, if you have been following on since the first episode, pat yourself on the back because building a hardware CPU is no easy task. And we managed to do it. We managed to build a full computer with RAM, registers, control unit, ALU, all of that. And of course, for those who are just joining in now, if you don't know what I'm talking about, go check out this full series. We're going to start from transistors and walk all the way up to pretty much all of modern computing. So stay tuned for more episodes. Now we're going to actually take a look at machine code, which is the lowest level of programming because it's the only language the CPU knows. The CPU doesn't know about assembly or C or Python. It just knows about ones and zeros, and we will see that today. So right now in this level, we're given this layout with all of these bit flags, this address kind of layout, and then we see the corresponding assembler instruction. And you might ask, this is kind of random. How do we programming this? But I will say we've dealt with this before. First, this layout is wrong because if we go back to this hardware level here, we see that the computer has this ROM component, and this ROM is actually stepping through. So when you press the clock, you can see the ROM being counted up. When we click edit ROM, there we go. That's the same layout as the level that we are currently on. And you might ask, well, what do these bit flags do? Again, we've also addressed that as well. If we go back to this processor instruction level here, we've seen that this splitter takes the 15 bits and then dedicates these bits to the ALU and these bits to the condition and stuff like that. And even bit 15 is addressed in the control unit. So everything is in there in hardware. So this isn't stuff that just came out of thin air. This was the stuff that we've built beforehand, but now we get to actually use them. So the first thing we're going to do is we're just going to do these 4 simple program instructions, and these don't really do anything, but it just shows you how to program in machine code. First, let's set the D register to 0. So we're just going to make D equal to 0. To do that, we need to set this 15th bit to be 1, and then we need to set the 0 flag to also be 1, because of course we're setting stuff to 0. But what are we setting to 0? Of course, that is register D. So D has to be 1. And there you go. You can see D equals 0. And the corresponding hex instruction is 8090. So that's how you kind of convert machine code into actual instructions, is you take it apart, break it into its bits, and then you do the whole ALU control unit thing that we talked about last time, and then the CPU runs it. All right, next thing we're going to do is we are going to look at how do we set A register to 2. So A register to 2, all we have to do is we're going to set the jump equal flag to 1. Now this might seem random, but the address is A. So the A register contains the address. And in this case, this address 1 corresponds to the decimal value of 2. So that's why you see in this assembler, we just have to set this equal flag and A automatically becomes 2. The third one we're going to do is we're just going to add 1 to the D register. So the D register is already 0. Now we're just going to add 1. So to do that, we of course, adding is an arithmetic operation. So we got to toggle the control bit to be 1. And then we need to actually use the adders. So keep in mind, this U flag toggles between logical and arithmetic. So we need to set U to be 1. And then we need to set op 0 to be 1. And finally, D to be 1. So now you can see D equals D plus 1. And the corresponding instructions is shown in decimal and hex. The final instruction that we're going to do for this level is to jump unconditionally, which means no matter what, just jump. And to do that, we of course are going to set this instruction here again, and then we are going to set the less than, equal to, and greater than. That is a unconditional jump because it doesn't matter if you're less than, equal to, or greater than. All of them will have to make you jump, and that's why it's unconditional. So let's just test this. Of course, D starts at 0, so I'm just going to make it a random number for now. So when we do this, it says will change to 0. But to run these instructions, we just execute the clock. So you can see our program counter is pointing at address 0, and we're going to run this 15 bits here, which will set D to 0. So clock tick, D becomes 0, PC will get incremented, and then just do this again. All right, now A is 2, and then D will be 1 now because we're going to add 1. And there we go. And then finally, we're going to jump. So there we go. It's just going to keep on adding because it's unconditionally jumping, and then it will run the instruction and jump again. And that should be the solution. There we go. Let's go on to the next level, because first of all, we've programmed in machine code, but it gets really, really hard to keep track of instructions that are more than like 10. Like if you have 100 lines of code, that'll get translated to who knows how many machine code bits there are. And that takes forever to actually implement correctly. And not to mention, you might make mistakes by setting the bits wrong and stuff. So that's why we need something called a assembler language. But this assembler language will translate all these operations into their corresponding bit flags, so that when we write, for example, D plus A, it will just set the bits automatically for us. So we don't have to worry about making a mistake or something like that. So we're just going to go through all of this. And I know there's a lot, but all of these are used. So let's just start. So with the blank opcode, which means we do nothing, we just set everything to 0 because, again, nothing's happening. We want to set A to equal to something. So A equal to something is actually the move instruction. So move something to A. That, of course, A is toggled. Otherwise, it's D. We're just going to quickly do this. Otherwise, star A. These bit flags accordingly. And then AD, just do the same thing. A and D get set. D and A star A get set, and then all three get set. So not that bad. This is just setting stuff for you to be able to move it. And of course, this corresponds to the destination. And then the calculation and then jump condition. So you can see we are breaking this instruction into 3 parts. All right, the calculation is a bit long, so I will do that last. Let's do the jump condition first. So again, same thing, blank, we don't do anything. Jump less than, of course, toggle the less than flag. Jump equal to, toggle the equal to. Jump greater than flag. Less than or equal to, toggle both of them. Greater than or equal to, toggle both of them. And then jump unconditional, which means I don't care if it's less than or equal to or greater than, just jump whenever. So there we go. That's what we pretty much did last time as well with that level. Now, the calculation. So we have a bunch of these calculations, but recognize that all of these are arithmetic or logical calculations. So this is dealing with the ALU again. So let's just do this really quick. So D plus A, of course, that is just setting U to be 1 because it's an arithmetic adder operation. And then, yeah, D minus A, same thing, set U to 1. But then we got to set op1 to 1 because it's subtraction. And then finally, A minus D, same thing. However, we got to switch them. So that's why we set the switch flag to 1. Let's see, A minus, yeah, that's A minus D. D plus 1 we just did. So 1, 0, 1, 0, 0. And then A plus 1 is 1, 0, 1, 0, 1. Yeah. And then D minus 1 is 1, 1, 1, 0. Again, you just look. If you don't know how I'm just remembering this, well, I'm just referring back to that ALU level. And keep in mind, if you build it, it will save your stuff. So, for example, if you just go back into this hardware here, under this ALU, you have all of these bits. That's why I'm just cross-referencing this chart right here. So that's all I'm doing. And oops, no new tab here. Let's close that. Go back to software, and then, okay, so let's continue. Minus D. So minus D is the equivalent to 0 minus D, of course. So that's just 1, 1, set that, and then 0, 1, 1, because we switch and then we set the 0 flag. Same thing with A, 1, 1, and then 1, 0. Negative 1 is a literal, but all we have to do is we just set op1 to 1, this, so it's just saying 0 minus 1. And then the literal 1 is just 1, 0, 1, 1, 0. And D, just to get D back, so like a identity operation, that would be 1, 0, 1, 1. And then A will be 1, 0, 0, 1, 0. Okay, now we're going to move on to the logical operations. So we have D and A. And instruction, holy crap, there was a lot of ands right there. But with the logical and, everything's set to 0 because that's just the first instruction. Again, refer back to the level with the ALU. The bitwise not instruction, that's 1, 1, 0, 0. And then the bitwise not for A is the same thing, except for we just toggle this to be 1 because we switch it. And then finally, 0 the literal 0 is just the 0 flag turned on. Everything else is 0. So there we go. You can see it's already kind of being annoying to go through all these 1s and 0s, and then like you gotta check a lot of times. So let's check to make sure we got it right. And of course, we all got something wrong. I told you programming in machine code is hard. So A-1, oh, I think we skipped that. That's why it's saying it's all zeros. So A-1 is actually 1, 1, 1, 0, 1. And then let's check again. And we also skipped D or A. So you can see it's kind of being annoying to program it because there's a bunch of 1s and 0s, and we gotta be careful so that we don't accidentally toggle something. So that is just op 0. And let's check solution. There we go. All right. So hopefully that illustrated how annoying it was to actually program in raw bits. And I really don't want to do this. So NAND game doesn't want you to do this either. So that's why the next level is assembler program. But I feel like if you want to continue with NAND game, you have all the stuff needed to continue. And by the way, there are a lot of levels here. So it does a great job of illustrating all the other stuff. For example, there's the stack, which we're going to talk about, and there's function calls and stuff like that. But I think this is a good stopping point because we've seen how machine code works. We've seen how NAND game can let us build a CPU from hardware. Now we're going to transition to industry-related things such as x86. So we're going to stop NAND game here, and we're going to basically graduate NAND game and move on to real-world CPUs such as, again, x86. So that will happen in the following episodes. Continue watching the playlist. We'll finally end with, again, all the stuff you're familiar with, high-level programming languages. But now we're going to transition to x86. And as we go to x86, just remember the stuff like if I go say, what's a move instruction? That's what this is. What's the jump instruction? That's what these guys are. And what's the add instruction? That's what these guys are. What's the logical and that's what this guy is. So all of these instructions, even though they're for 64-bit instead of 16 bits, like what NAND game does, it's literally the exact same thing. It's the exact same format. It's the exact same operation. And it's just, again, done for x86, mainly because x86 is used in real life. So hopefully this kind of shows you how to program stuff inside what a CPU understands, which is machine code. And if you really want to know how to program in assembly, we're going to do that in the next episode. So stay tuned.